Hey Grant, how's it going, man? I hope you're doing well. Thanks for coming to my presentation today on Desert Varnish by Luke Marshall. So, what is desert varnish? Well, some general information that we know about desert varnish is that it's orange to dark brown to even black in color. We find it on high angle, arid environments such as cliff sides in the desert, which we have a lot of. And some people think it's a black stain on the rock, which we will talk about, and how it is not a black stain on the rock. You absolutely have to have clay present in order for the varnish cycle to start. And this clay creates a really awesome environment for microbial organisms to grow and live. And once the desert varnish has set, winds blowing sand and dust particles around basically polish the desert varnish, and that's why, generally speaking, it's like a shiny splotch on cliffs. Around here, there's sandstone cliffs most of the time, and desert varnish. There's two different types of desert varnish. There's iron oxide desert varnish and manganese oxide desert varnish. And here in southern Utah, we generally find higher concentrations of manganese oxide desert varnish. So that's what we'll be discussing today. So here are some photos of desert varnish, and as you can see, both of the photos follow all of the guidelines that we just spoke about on the last slide. Um, they're high angle, they're cliffs, there's no plant life or anything, and they're dark. They look like stains on the rocks. Looks like stains, like this one looks like a waterfall stain. We see them a lot where we see water, because you have to have intermittent water flows in order to have clay accretion for these microbial organisms to start to thrive, colonize. Clay in desert varnish. Well, first you have to have clay to have everything else. So that's why we'll talk about it first. Um, it is varnish is not able to form without moisture. I guess I should have said that. You have to have water before you have anything else, because the water the clay sticks to the water, this dust blowing around in these arid environments. It sticks, it accumulates, it turns into a type of clay, which is only a few micrometers thick. And that's why people have thought, and still maybe think, that the varnish is coming out of the rock, because you're not able to actually really see this accretion taking place. And if you put your hand across the rock, you wouldn't be able to feel a difference between the normal rock and the varnish. Maybe one would be a little more smoother, the varnish perhaps. But other than that, it's hard to tell the difference in thickness. And but there's a clear boundary between the varnish surface, the varnish interface, which is the body of the varnish, and the rock interface, so where the varnish is accreting on. And this discovery was found through scanning electron microscopy, also known as SEM. So here's some photographs of SEM, images that SEM machines have found. And as you can see, this one in particular, there's a clear distinction between the rock interface, the varnish body, and then the varnish interface. Okay, so you can clearly see there's a separation, and it's clear that the varnish is separate from the rock. It's not coming out of the rock, it's being accreted onto the rock. The other pictures are show similar, the same things, but they're a little harder to see, because this varnish is so thin. It's so incredibly thin, you can't see it with the naked eye. Here's a picture of an SEM machine, a scanning electron microscope. Big piece of equipment, really fancy, really fun. So, next we have the microbial origins of desert varnish. So this clay has been deposited, and we already talked about the water and the clay. So this creates a moist environment that is extremely favorable towards microbial organisms. These microbial organisms colonize, and they start to secrete manganese oxide, and we start to see a buildup. And the bacteria attached to the clay, we have seen this through the SEM, and we've also observed through the SEM machines an extreme concentration of manganese oxide. And when I say extreme, we see manganese oxide build up and concentrations, but when we see it on desert varnish, we see it past those levels that we've ever seen in other circumstances. So we know that we have to have something depositing this. It's not just seeping out of the rocks. It's not just being accreted with the clay. So and then so it must be a bacterial origin. And we see that this bacteria can only survive in a neutral pH, which is why it likes cliffs, and you don't see it next to a yucca plant, because plants and lichen can, and also acidic rain can change the pH of water, killing the microbial organisms, leaving the desert varnish unprotected because it doesn't have its manganese oxide like cap and finish. And so the varnish, once lichen starts growing, the varnish starts to disappear, and it's dying, basically. Here are some microscopic photographs of the bacteria with the manganese oxide. You can see that there is something living in this desert varnish. So, if we know these fun facts about desert varnish, then the next logical progression is, how old is desert varnish? And now, why would we want to know this? Well, the main purpose of learning out how old desert varnish is because of petroglyphs. Petroglyphs are Native American or indigenous depictions of things, and they're pecked into rocks. And normally, in the past, we see that these petroglyphs are on desert varnish faces because of the color contrast of this black desert varnish with this red sandstone. So we know the law of superposition. First we had the wall, then we had the desert varnish. So the desert varnish has to be older than the wall. It can't be younger than the wall or the cliffside. So then we look into radiometric dating. Well, and so what they did, some scientists, is they looked at the Shinnerup conglomerate near Hurricane, Utah, which is cool to find these really close places in these really upper level geology papers. But anyways, they looked at this. They found that it's the desert varnish, the altered rine of the rock, and then the heart rock. So where the desert varnish is growing on the heart rock, it's actually changing the chemistry of the rock a little bit. But they're looking for the desert varnish, and so they found some. They were able to test it. And what they found from that, they found a number, and then they tested the heart rock, and they found the same number, which means that the daughter isotopes are escaping while they're doing this radiometric dating. Not while, but previously while it's aging. And so the data is inconclusive, and they still don't know how old desert varnish is. Here are some petroglyphs, and it's very clear there's desert varnish, and these petroglyphs are popping because of the color contrast with the rock. And so yeah, we see desert varnish all over southern Utah and even all over the world. And it's so crazy that in these huge sandstone playgrounds where we're watching weathering and erosion before our very eyes, that we're actually seeing accretion as well. These things are growing and being accreted onto these cliff faces. So next time you go outside, have a little bit more appreciation for that brown stain on the rocks. Thank you.